Hello everyone, I hope you're all doing well. So we're going to be solving a problem on particle kinetics, and this is going to be in the curvilinear system. Okay, so here is the situation. First of all, we consider this fixed semi-cylindrical surface here. Okay, so this is a fixed surface. So I'm just going to label it. So fixed surface, and then I have a pinned point, okay, at this point O, and then I have this rod OA, okay. So this rod OA, which is initially placed in the position that is shown, and then there is a particle which I'm going to call as the particle P, okay, which is placed on this rod. And then what happens is that this rod is now going to start rotating at a constant clockwise rate, okay, starting from where it was originally defined. Okay, so after some time the position of the rod becomes the following. So I'm just going to copy this. Let's say I'm going to copy this and I'm going to paste this, and the position of the rod after some time, let's say the rod is somewhere here. Okay, so this is where the rod is going to be after some time, and this particle, which is probably sitting along with the rod and going for the ride, is also going to be I guess I need to make it a little big and then come back and then reduce its size. Okay, so the particle is probably going to be here. Okay, so this is the rod OA at some other point in time, at some arbitrary point in time. Okay, so this is at some arbitrary time. Okay, which means that this rod is rotating at a constant clockwise rate, and let's give some variable names here. Okay, and so first of all, let me say that the location of this rod, so initially this is at an angle of 90 degrees, as you would have seen here, right? But then after some time the location of this rod becomes the following. Okay, so this is a situation where we are at. Let me say that the radius of this semi-cylindrical surface is a constant value, capital R. Okay, so let's say that R is the radius of this surface, and here is also where the center of that semi-cylindrical surface is. Okay, and let me call this angle here, starting from here all the way down to there. Okay, let me call that angle as an angle phi. Okay, and let me call this angle here as an angle theta. Okay, so what are the things that we are supposed to be doing here? Okay, so first of all, here is a particle P at some arbitrary point in time. This is the initial position, of the rod OA. Okay, and this is at some arbitrary point in time. Let me scoot this down a little more. Okay, so the particle P travels as shown on the fixed surface. Okay, the rod OA has a constant, okay, clockwise rotational rate of 0.87 radians per second. Okay, and then we will also say that, okay, the mass of the particle m is equal to 1 kilogram, and let us also say that the radius of the fixed surface is 1 meter. Radius of the fixed surface, which is capital R. Okay, this is equal to 1 meter. Okay, so the mass is given, the radius is given to us as well. This rod is rotating at a constant rate, and so if phi denotes the location of the rod at any point in time, then the rate is going to be given as you could have guessed it, phi dot. Okay, so which means that this 0.87 radians per second is phi dot is equal to 0.87 radians per second and constant. okay, in the clockwise direction, okay, and the mass of the particle is given, radius of the fixed surface is also known to us. What are the things we need to do? Okay, so here are the things we need to do. Okay, so at some arbitrary point in time, at some arbitrary position of the rod OA, obtain the force balance equations for the particle. Okay, that's the first thing. And then the second thing is determine the angle phi at which the particle starts to leave the circular path, at which the particle leaves the circular path. Okay, so a couple of key things here. So that is a little darker than I needed. Okay, a couple of the key things here. So at some arbitrary position of the rod OA, okay, we need to obtain the force balance equations. Okay, which means that we need to choose a coordinate system and then we need to sum forces in both the directions. It's a two-dimensional problem, of course. Okay, then we also need to determine the angle phi at which the particle leaves the circular path or the surface. Okay, so if I go back and look at my figure here, so this could potentially be the following. Okay, so let me maybe draw this rod OA again. So I'm going to copy that and paste that, and let's say so it's probably, I don't know, somewhere here. It's all the same length, of course, right? Let me maybe reduce its length to begin with. Okay, so it's slightly longer here, as you can see. Then it gets slightly shorter because you're looking at it from the perspective of the point O, and then at this point probably it is here. And then what you'll see, let me not mess up the figure there. So what you'll see is that this particle, okay, which was initially here, okay, so if I copy that and if I paste that, I guess I wanted to move this guy, but I can still do that. Let me reduce the size. All right, that looks more like a particle. This looks more like a sphere. Okay, all right, so here is that particle. So it's probably now here. Okay, so the particle has now left the circular path. Okay, so this is the angle phi at which the particle has left the circular path. Okay, so at this position the particle leaves the circular path. So even though the particle leaves the circular path, right, it is still in contact with this rod OA. Okay, one of you mentioned this new feature to me while I was doing office hours the other day, so I'm going to be making use of that. Okay, thank you for telling me that, Pantelis. Okay, so this is OA here. All right. So it's a nice, interesting problem. I need to find the angle at which it loses contact with the surface. And so the first thing is, I need to find the equations of force balance. Okay, that's the first thing. And then second thing is, what is the angle at which it leaves the surface? Okay, so my solution. So in terms of my solution, I'm going to do the following. Okay, I'm going to first of all copy this figure down, and I'm going to do some basic geometry. So I'm going to copy this figure, I'm going to get rid of a lot of things, and I'm just going to look at it from an arbitrary point. Okay, so first thing is look at the situation, look at the particle plus the rod OA at some arbitrary position, and then set up a coordinate frame. Okay, so my choice here is the polar system. Okay, so that is you can also solve this using the normal tangential, but my aim is, I'm asked to find out the angle phi at which it leaves things, which means that phi, as you can very well see in the figure here, phi is a polar angle, right? Because I'm sitting at the point O, which is a fixed observer right at this point, and so I can observe the proceedings as such. Okay, so I'm going to set up, so I shall set up a polar coordinate frame. Okay, with a fixed observer at O. Okay, so this is what I'm going to be doing. With a fixed observer at the point O. Okay, so important thing is that this is a polar coordinate system and the observer is a fixed observer. Typically, whenever you set up a coordinate frame, always choose some kind of a fixed observer. Okay, so let me maybe scoot the statement on slightly more to my left so that it aligns with what I have written here. Okay, all right, so here is probably my figure, which I'm going to copy again because I did other things that I was not planning on doing. Okay, all right, so here is my figure. I'm going to clean this figure up. Okay, with your permission, I'm going to get rid of many of these things. So first of all, I'm going to get rid of all of these words that I have. Okay, we know what these things mean. Okay, then I'm going to get rid of this particle which was initially here because I'm not interested in that at that point in time. I'm interested in some arbitrary location, as you see. Okay, I'm going to get rid of that as well. Okay, which means that I'm going to get rid of this guy who's hovering in the air. Okay, so here is my system. Okay, so choose the polar coordinate frame starting from the point O all the way to there. I know that this is phi dot and so on, so I'm going to get rid of all that as well. I'm going to get rid of this as well, so I have a nice clean figure here. So this is theta. Now I know that the distance from, let me call this point as the point let's say B. Okay, so let me go back to point B here. Once again, thank you Pantelis for pointing that feature out. It's pretty useful. Okay, so OB is also of the radius R, as you can see, which means that the triangle OBP is an isosceles triangle. Okay, so triangle OBP is an isosceles triangle. Okay, so that is good news, which means that this angle here is also going to be the angle theta. Okay, which means that this entire angle, I'm going to get rid of this horizontal line in the middle. Doesn't do any world of good to me. Okay, as you can see. So this angle here is going to be 180 minus 2 times theta, as you can see. Okay, so starting from the point O, which is my fixed observer here. Okay, so this is my fixed observer. Okay, I'm going to set up the polar coordinate frame. So from point O to where the point P is located is a distance r of t. Okay, so r of t is the distance from O to particle P. Okay, and then phi is also a function of time. Phi is the angle measured from the y-axis. Okay, so phi of t is measured from the y-axis. Okay, and this denotes the also the rate at which the bar OA or the rod OA is traveling. Okay, now with all these, I'm going to do some basic geometry, but before I do that, I need some coordinate frames, right? So first thing first. Okay, so I'm going to take this A guy and then bring him here. Okay, and then let me choose a different color. So let me choose the blue color here. So starting from point O, I'm going to have a radial coordinate frame. Okay, so which means that this is going to be the E suffix R direction. Okay, and then I'm going to have the E theta direction. Something that you want to keep in mind, or I'm going to have the E phi direction, of course. not E theta. And E phi is chosen in the direction of increasing theta, which means that the direction of E phi is going to be pointing this way. It is not necessarily tangential to that path. Okay, so this is the direction of E phi. Maybe let me reduce the size of this guy a little lesser. Okay, all right, that's good. Then this is going to be E phi. Okay, so let me also write that out. Okay, so E phi, maybe I have some space here. So the vectors, unit vectors are E r and E phi. Okay, and E phi chosen in direction of increasing theta, increasing phi. Increasing phi. Okay, so that's something that is important as well in this particular problem. Okay, so I have my unit vectors chosen, I have my coordinate system chosen as a polar coordinate system. Now let me do some basic geometry, because I like geometry, because it looks like an isosceles triangle. This is really good news for us. Okay, so I'm going to make use of the sine rule. From the sine rule, I can say the following, right? I can say, so law of sines, okay? So from the law of sines, I can say that r of t divided by the angle opposite to r of t, which is sine of pi minus 2 theta. This is equal to capital R divided by sine theta. Okay, so that is the first thing. Okay, and from this I can also say that, okay, if I do the cross multiplications and so on, then I can get, and sine of pi minus 2 theta is sine 2 theta. Okay, so this essentially tells me that r of t is equal to r times, if I cross multiply, this is sine of pi minus 2 theta, all of this divided by sine theta. Okay, which tells me that r of t is equal to r times sine of pi minus 2 theta is the same as sine 2 theta. So aside, sine of pi minus 2 theta is the same as sine 2 theta. It's in the second quadrant. Okay, and so this is going to be the following. So this is sine 2 theta. We have the formula for sine 2 theta is 2 sine theta cos theta. Okay, so these are the formula for that, which means that this is going to be 2 times sine theta cos theta, and this is divided by sine theta. Okay, which essentially tells me that, okay, I can cancel off one of the sine thetas from here. So this is cancelled off and that's cancelled off. Bad habits, I keep going back to my color palette there, where I can do that here. So I'm trying to get used to it still. Okay, so this means essentially that I can say, okay, r of t is equal to 2 times r times cos theta. Okay, so that's one piece of good news. I can do something more. Look at this. Let me go back and get my black color. One more thing that you can see from the figure is that phi plus theta is equal to 90 degrees. Okay, so this was law of sines. I just want to underline that as well. Okay, where we have used some geometry, and then I go back to my figure and I can take a look and see that phi plus theta is equal to 90 degrees. So from figure, or from triangle or figure, we can see that phi plus theta is equal to pi by 2. Okay, which means that phi is pi by 2 minus theta. Because I want to write everything in terms of phi, I'm going to do the substitutions here. Okay, so essentially I go back here and then I say, okay, instead of theta, I can write this as r of t is equal to 2 times r times cosine of theta, which is pi by 2 minus phi, right? This is because we know that phi plus theta is equal to pi by 2. Okay, so essentially this is what I have here, but cosine of pi by 2 minus phi is sine phi, so which means that I now have a relationship between r and phi. Okay, so this is going to be 2 times r times sine phi. Okay, so now we have a relationship. Okay, so this is an important thing. So this is relates r of t to phi of t. Okay, which means that I'm going to do the differentiation of this quantity. Okay, so differentiate with respect to time. Differentiate with respect to time, and then I get dr by dt. This is equal to 2 times, so let me do this carefully, d by dt of 2 times r times sine phi. Okay, now I'm going to use the chain rule, okay, and then the product rule. So first of all, dr by dt, which is equal to r dot. Okay, this is equal to 2 times, capital R is a constant, so I'm not going to do any differentiation of that. So this is going to be, and you can maybe let's do it this way. So this is going to be dr by dt times sine phi plus 2 times r times d by dt of sine phi. Okay, and obviously dr by dt is 0, so which means that that guy can be gotten rid of. Okay, and then I can say, okay, hey, r dot is equal to 2 times r. Look at this, d by dt of sine phi, use the chain rule. This is d by d phi of sine phi, d phi by dt. Okay, where I have used the chain rule. Okay, and d phi by dt is phi dot, and d by d phi of sine phi is cosine phi. Okay, so which means that r dot is equal to 2 times r times phi dot cosine phi. Okay, so that is another important piece of good news there, or useful information. And then I'm going to go forward and then do the differentiation one more time with respect to time. Okay, so differentiate once more. I need to go back to my regular color. Okay, all right, still getting used to it. Okay, differentiate with respect to time once more. I'm going to be getting d by dt of r dot is equal to d by dt of 2r phi dot cosine phi, and I'm doing this slowly step by step because some of you wanted me to go through some of these details. Okay, so here is what I get. D by dt of r dot is r double dot. Okay, and then I'm going to use the product rule and then the chain rule. So 2r is a constant, so I'm just going to bring that out. So this is going to be d by dt of phi dot times cosine phi plus 2r phi dot d by dt of cosine phi. Okay, which is going to give me the following. So this is r double dot is equal to r d by dt of phi dot is phi double dot. I don't need to use any chain rule there, but I need to use the chain rule here. So this is 2 times r times phi dot d by d phi of cosine phi d phi by dt. I hope this makes sense. Okay, and so here is what I end up getting. So r double dot is going to be 2r phi double dot cosine phi, and then d by d phi of cosine phi is minus sine phi, so this is going to be minus 2r phi dot square of sine phi. Okay, so these are the 3 things that I have. So I'm going to just collect all the information that we have so far. Okay, so let me go back to my regular color. So information so far, so the equations we have so far. So we have the following. Okay, so I'm just going to bring out all my big guys, starting from this guy here. So I'm going to bring that, so copy that, and then bring it down here. Okay, I don't need that pesky little thing there. Then I need this one here. I'm going to copy that, and I'm going to bring that here. Okay, and then I'm going to bring this big guy here. I'm going to copy that, and I'm going to bring that here. But you know what? I'm told in the problem, okay, if I go back to the problem statement, Okay, I'm told that this phi dot which I had here is a constant, right? You see that, right? So phi dot is a constant, which means that phi double dot is equal to 0. Okay, so but we know, okay, so this is what we have so far, but we know, I'm back to my color, that phi dot is a constant, which means that phi double dot is equal to 0, which means that I can get rid of this entire term here. Okay, which means that I can rewrite my r double dot in a much nicer way. Okay, so this tells me, okay, that r double dot is equal to minus 2r phi dot square sine phi. Okay, so let me put a blue line underneath that as well. Okay, so what am I going to do next? Okay, so I've done some basic geometry and so on. Then I'm going to bring out the polar coordinate frame. Okay, in the polar coordinate frame, we know the following. Okay, so in the polar coordinate frame, okay, so for us, this is the unit vector system ER E phi. We know from kinematics that acceleration is r double dot minus r phi dot square ER, and then 2r dot phi dot r phi double dot E phi. Okay, so this acceleration is the radial component of the acceleration. This is the transverse component of the acceleration. So which means if I take a look at this radial component, so this is r double dot minus r phi dot square. Okay, I'm going to start substituting. Okay, so AR is this much, and then A phi is 2r dot phi dot r phi double dot. But I know that phi double dot is 0, right? From previously here, we know that phi double dot is equal to 0, which means that this phi double dot term can be cancelled off. Okay, and then I'm going to start substituting. Okay, so start substituting. Substitute for r dot and r double dot in terms of phi of t. Okay, which tells me that, okay, AR is going to be the following. So r double dot is minus 2r phi dot square sine phi, and then minus r, which was if I scoot back, r is 2r sine phi, so this is going to be 2r sine phi, and then one more phi dot square. Okay, which essentially tells me that, okay, hey, AR is going to be minus 4r phi dot square sine phi. This is beautiful. Okay, this is very crucial and very interesting. Okay, and then likewise, I can say that, okay, a phi, which is 2r dot phi dot, is going to be 2 times phi dot times r dot, which if I scoot back up is 2r phi dot cos phi. Okay, which tells me that a phi is going to be 4r phi dot square cosine phi. Okay, so these are 2 important things that I have found out. Okay, and then what do I do now? So once I'm done with the kinematics part of the problem, so this is all the kinematics and the geometry part of the problem. Once I'm done with this, then I go back and look at my free body and kinetic diagram. Okay, so my next step, draw the free body diagram and the kinetic diagram at some arbitrary phi of t. Okay, this is fairly straightforward. Let me go back and bring my good looking figure. Okay, I'll write this guy here. Okay, so this beauty is going to come down, and we're going to make use of this ER and E phi system, and then draw the unit vectors for that. okay, and the free body in the kinetic diagram. So let me bring that here. Let me keep that creature right here. I think I have enough space for the free body diagram here, so let me maybe copy this guy here. Let me copy that and paste that a couple of times. Okay, copy that and paste that one more time. So free body and kinetic diagram. Then I'm going to have this ER, copy that and paste that here. Okay, all right, this is okay, so this is my ER direction. I'm going to have my EF direction, copy that and I'm going to paste that here. Okay, and likewise I need both of these, copy and paste onto the kinetic diagram. Okay, so I'm going to have my free body diagram here, and then I'm going to have my kinetic diagram here. Okay, kinetic diagram is fairly straightforward because all I need to do is just mark the acceleration. So let me do that really quickly. Okay, so let me do that. Let me also underline this guy here. Okay, and then he'll feel left out. Okay, I'm going to mark the accelerations, mass times the acceleration. So this is going to be mass times acceleration in the radial direction. So this is m times AR, and then obviously this is going to be mass times acceleration in the transverse direction, so that is m times a phi. Okay, so this is the situation here. Then what else do I have? I go back to the free body diagram. What are the components in the free body diagram? First of all, I have the weight of the body. Okay, so the weight of the body is going to be acting vertically down. Okay, so this is going to be mg, and it is very obvious to see that this angle here is going to be the angle phi. Okay, if I draw a vertical line right on the particle p, if I can do that on the figure right here. Okay, I need to get rid of this guy and bring that particle p maybe down here. If I draw a vertical line here, okay, by basic geometry, I can find out that this angle is also the angle phi, because I have two parallel lines and then their corresponding angles. Okay, so this is the ER direction. So if I take this mg, I'm breaking it into its component. Let me do that very quickly. Okay, so there is a component this way. Okay, so that's going to be mg times cosine phi. Okay, so mg cosine phi, and then I'm going to have a component which is mg sine phi in this particular direction. Okay, this is going to be in the E phi direction. So let me get back to my figure here. So this is mg sine phi. Let me reduce the size of this guy so that I have some space to write it out. Okay, apologies for that. So this is going to be mg sine phi. What else do I have on this free body diagram? Important thing, I have a normal force acting on this free body diagram. Okay, there is a normal force of contact between the surface and the particle. Okay, so I'm going to write out those things here. So there is a normal force N between the surface and the particle. Okay, this will be along the line BP. Okay, I hope that makes sense. And then there will also be a contact force between the rod and the particle in the EF direction. So that is also an important thing. So I need to have some space to write it out. So let me bring this guy. Okay, let me bring this guy and then cut that and bring that down here. So that's one thing here. So there is a normal force. Okay, then there is also going back to my same color. Okay, there is also a contact force, let's say FC, between the rod OA and the particle along negative EF. Okay, and so I'm going to mark these forces right down here. So let me say, okay, there is first of all the normal force. The normal force is going to be pointing along the line BP. So which means that if I take this line here and if I extend it here, right, then my normal force is going to be pointing this way. Okay, so this is my normal force, which means that this normal force is also going to have components along E phi and ER. Okay, this angle here is the angle theta, as you can see from the figure there, right? So theta is pi by 2 minus phi. So this angle is actually pi by 2 minus phi. And so I can say that the component in this direction for that normal force is going to be the following. Okay, so this is going to be n times cosine of pi by 2 minus phi, or n sine phi. So this is n times cosine of pi by 2 minus phi. This is one force. There is also another force here. There is one more force which I'm going to be drawing in a second. Okay, and this is going to be n times sine of pi by 2 minus phi. And then my last force, which is going to be the contact force, which I'm going to be drawing right down here. Okay, so let me draw the contact force as well. Okay, which I'm going to call as F suffix C. Okay, so this is my free body diagram, and this is my kinetic diagram. So lots of things going on, which means that I'm going to clean up my free body and kinetic diagrams, and maybe just keep some of the things going on here. So maybe before I do that, let me try cleaning up the same figure here. Okay, so I'm going to take these two figures. These are my free body and kinetic diagrams, and I'm going to bring them down to the next page. Okay, because I want to write my force balance for these things. So here I can get rid of all of these guys. I don't need them because we already did that. Okay, so this is going to be the components of the weight in one direction. Then I'm going to get rid of all of these guys. Apologies. I'm going to get rid of all of these guys. Okay, cut that off, and then recognize that cosine of pi by 2 minus phi is sine phi. Okay, so I'm going to get rid of that guy and then write him as sine phi. So sine of pi by 2 is cosine phi, so I'm going to get rid of that as well. So this is going to be cosine phi here, and then this is going to be sine phi right there. Okay, and then of course I have the contact force as well. So these are the forces on my free body diagram, forces on my kinetic diagram, and then we also know from before. Okay, what are the things that we know from before? If I go back, scoot up to the figure, I know AR and A phi. Okay, so I'm going to bring up AR, copy this guy, then I'm going to bring that guy here. Then one more thing I got to bring is A phi. Okay, so copy that, and then bring that down here. And then we further know that R is equal to 1 meter, phi dot is equal to 0.87 radians per second, and then the mass m is equal to 1 kilogram. Okay, all I'm going to do now is sum up forces in the ER and the E phi direction. Okay, so let's do that. So sum of all the forces, so force balance. Okay, so sum of all the forces in the radial direction on the free body diagram, okay, where this was the positive radial direction. This is equal to sum of all the forces in the radial direction on the kinetic diagram. This is the positive kinetic diagram radial direction. So what are the forces in the radial direction? Look at this. I'm going to have n sine phi, mg cosine phi. Mg cosine phi is pointing in the negative radial direction, as you can see, and then n sine phi is in the positive direction. So I'm going to have n sine phi minus mg cosine phi. Okay, this is equal to m times AR. Okay, this is equation 1. Likewise, I'm going to have sum of forces in the transverse direction on the free body diagram. This is equal to sum of all the forces in the transverse direction on the kinetic diagram. Okay, and then I'm going to say, okay, this is my positive transverse direction, positive transverse direction. What are the forces? Look at this here. Transverse direction, I have the contact force, which is FC, then I have the normal force n cosine phi, then I have mg sine phi. Mg sine phi, let me write the sign properly. So mg sine phi minus fc minus n cosine phi. This is equal to m times a phi. This is equation 2. Now start substituting. Okay, so substitute for AR, A phi, M and R into equations 1 and 2. Okay, so let me do that. So these are my force balance equations. So eventually, after I do the cleanup and all that, I get the following. So this is going to be N sine phi minus G cosine phi. This is equal to M times AR, okay, where AR was 4R phi dot square sine phi. R is equal to 1, so this is minus 4 phi dot square sine phi, okay, where we said that M is equal to 1 kilogram and then R is equal to 1 meter, okay. And then likewise, so this I'm going to call as equation 3. And then I'm going to have equation 4, okay, which is going to be mg sine phi, which becomes g sine phi minus fc minus n cosine phi. This becomes equal to m times a phi. M is equal to 1. A phi is 4r phi dot square cos phi. So that's going to be just 4 phi dot square cosine phi. Okay. So 3 and 4 are the force balance equations. Alright, so we're almost there. Okay, so I'm just going to underline these guys. So this is one crucial equation, and then this is the other crucial equation. Okay, then I go to the next part of the problem. Okay, so when particle, and these are the force balance equations, of course, which I have underlined here. Then when the particle loses contact with the fixed surface, we know what? We know that the normal force is going to be 0. Okay, so which means I revisit my force balance equations. Okay, so what are my force balance equations? And then set n is equal to 0 in them, which means that, if I look at equation 3, n is gone, so which means I'm going to have minus g cosine phi is equal to minus 4 phi dot square sine phi. And then what else do I have from equation 4? This is from 3. I'm going to have the following, and then from 4 I'm going to have the following. Okay, so this is going to be g sine phi. Okay, and this is going to be minus fc, and this is 4 phi dot square cosine phi. Okay, so these are my equations here. Now we know already that phi dot is 0.87 radians per second, which means that, if I call this equation as equation 5, and then if I call this as equation 6, then from equation 5 I can see that g, and let's say that g is maybe 9.8 meters per second square. So let me do the substitution, and the negative sign the negative sign goes off, so this is minus g cosine phi. Let me maybe write it out here. So phi dot square sine phi, which tells me that 9.8 times cosine phi is equal to 4 times 0.87 square times sine phi. Sine phi by cos phi is tan phi, so tan phi is going to be 9.8, all of that divided by 4 times 0.87 square, which means that phi, which is phi at loss of contact, which I'm going to call as phi suffix c, which is the angle at which the particle leaves the surface when n is equal to 0. Okay, so which tells me that tan phi c is 9.8, all of that divided by 4 times 0.87 square, or phi at the contact is around loss of contact is around 72.8 degrees. Okay, so this is the angle at which it loses contact with the surface. Let me bring that creature up a little bit. And what do you know, you can also do the following. Can also calculate, okay, from equation, let's say, what is this, equation 6. Okay, so from equation 6 we can calculate the contact force between the rod OA and particle, okay, and the particle P at phi is equal to phi C. And what is that going to be? Okay, if I go back here, so I have G sine phi minus FC. So I have G sine phi, which is now phi C, minus FC. This is equal to 4 phi dot square cosine phi C. This is from equation 6, which means that FC is going to be G times sine phi C minus 4 phi dot square cosine phi C, and if you do the substitutions and so on, you'll end up getting the following. Okay, so FC is equal to 9.8 sine 72.8 minus 4 times 0.87 square cosine of 72.8, which is a very small number, which tells me that FC eventually is going to be 8.5, approximately 8.5 newtons. Okay, so this is the situation. All right, so this is a fantastic problem. Okay, so very briefly, if I go back to my problem, I look at it. Okay, here was the problem. The particle is sitting here at some arbitrary point in time. We set up the unit vectors in the normal, in the radial and transverse coordinate frame. You could also do it using normal tangential, but then your observer is going to be at the point B, not the point O. Okay, then I do the force balance equations, typically looking at the contact force and then normal force. Once we get the force balance equations, we made use of some geometry to get this AR and A phi. And then once you do the force balance equations, then you're pretty much done with the problem. You just set n is equal to 0 to get the angle at which it loses contact with the fixed surface. Once you do that, you get the numerical value for that. You can also calculate the contact force between the rod and the particle. All right, I greatly appreciate your patience in hearing through me. This is a difficult problem in my opinion, but it's well worth the time and the effort. All right, thank you, and take care of yourselves. Bye-bye.